This is AP Calculus reviewing for the year. This is question 10 of the problems that were released from the AP Classroom website. During the time interval from 0 to 4.5 inclusive, water flows into tank A at this rate in liters per hour. During the same time interval, water flows into tank B at a rate of B of t liters per hour. Both tanks are empty at the beginning. The graph of y equals a of t and y equals b of t is shown in the figure above. They intersect here at k and here at 2.416. How much water is in tank A at time 4.5 seconds? Well, to find out how much water is in the tank, you have to know how much water you start with, the initial value, and then how much water is added. Now we're told that the tanks are empty at time 0. So this is not entirely necessary. I just think it's good practice because this is the initial value plus how much you're adding. This initial value is 0. If you put into your calculator, integrating this function, put it into y1, from 0 to 4.5, I believe you're going to get 66.532. This is measured in liters for a couple reasons. One, this is measured in liters per hour. This is measured in hours. The hours cancel, so you're in liters. If you choose to write a sentence answer, which I think is wise, at time 4.5 hours, tank A contains 66.532 liters of water. B, during the time interval from 0 to k inclusive, so k, once again, is this spot right here, which we don't know what that number is. Water flows into tank B at a constant rate, so it's linear, 20.5 liters per hour. What's the difference between the amount of water in tank A and the amount of water at tank B at time t equals k? Well, we first got to figure out when is k. Now notice, at k, they are both the same. So what I mean is they're both flowing in at the same rate. That's what I mean. We know that if tank B is flowing in at a constant rate of 20.5 liters per hour, and at this point right here, K, they're flowing in at the exact same rate. If we set A of T, which is this right here, equal to the rate that it's equal to, and solve for K, we could figure out what K is. I replaced the T's in here with K's. Put this in your calculator, put this into Y1, put this into Y2, do second calculate intersect, and you would find that it's 0.892 hours. Now that's just to start the problem. Because once we know what K is, then we can answer this question. During the time interval from 0 to 0.892, water flows into B at a constant rate of 20.5. And what's the difference between tank A and tank B? Well, if you look here, here's tank B, here's tank A. Tank B is definitely going to have more in it because at the beginning, it's going to have more in it at this point. It's pumping in more water. So that's why I put B first. This is B's rate. We subtract from that A's rate. We don't need to write the number here, 0.0892 or 0.892. You can if you want, or you can just write K because it's cleaner. So put this in your calculator. This is 20.5. This is function A. And what I would do in my calculator, I would type in into like Y3, 20.5 minus Y sub 1, because it's likely you already had this typed into Y sub 1. Or you could even go Y sub 2 minus Y sub 1 in here. Anyhow, graph it and then integrate from 0 to 0.892, and I believe you're going to get 10.599. At time t equals k, the difference between the amount of water in the tanks is 10.599 liters. Part C, I copied the picture down here. The area of the region bounded by the graphs of A and B from K to 2.416 is 14.470. So this blue region is the area that's bounded by them. Bounded means the boundaries that the part has are the two graphs. Here's K, and here's 2.416. This blue area is 14.470. How much water is in tank B at this time? So we want to know this area right here. That's what we're trying to figure out. So how I started this, and there's different ways you could start this, I wanted to focus on this 14.470. This 14.470 is the area under A minus the area under B. Because you find the area under A, that's this entire area. But we don't want this part, so we're going to subtract it away to get the blue area. So if you take the area under A, subtract the area under B, you could write this as 1. Well, no, don't write it as 1. And it tells us that area up here is 14.470, so you set it equal to that. Using a calculator, I can find the area under the curve of A from K to 2.416. Keep in mind, K we found was 0.892. So using a calculator, I got 44.497. If I subtract that from both sides, I get this number. These are negatives, so if I multiply both sides by -1, here's what I find out. The area under curve B from K to 2.416 is 30.027. That's this red area right here, which does not answer the question, but it tells us how much there is from here over to here. So then we are supposed to get the rest of this area. Let me color code the rest of this area. We want the green and the red area because that represents the area under curve B from 0 to 2.416. So tank B, you could think of it as the area under the curve from 0 to K, and then the area under the curve from K to 2.416. Now we were told initially that this was coming in at a linear rate of 20.05 from 0 to K. So this is the rate that it's coming in. That's why I have that there. Plus this area, which we found up here, and we know that to be 30.028. If we integrate this, we're going to get 20.5 K, or T, I should say. If you evaluate it from K to 0, putting 0 into this is going to just cancel out, so I didn't even write it. If you put K into this, which is 0.082, you get 18.286. So this green area is 18.286. This red area is 30.027. Add those together, you get the area of tank B, the amount of water from here to here, is 48.313. Last part. During the time interval from 2.7 to 4.5 inclusive, the rate at which water flows into tank B is modeled by this formula right here. In liters per hour again. Is the difference of W and A increasing or decreasing at this time? Well, to figure out what something's increasing or decreasing, all we got to do is look at the slope. So we take the derivative of this, and you don't have to do this. This makes more sense to me. I defined a new function, D is the difference, as being W minus A. And you could leave that out entirely and just do what you see here in green and receive all the points. I added that D of T to the problem because it makes more sense to me. So anyhow, so I set D equal to this, and then to figure out if it's increasing or decreasing, you want to find the slope. So to find the slope, we take the derivative. So the derivative of W and the derivative of A. Now keep in mind, I would have this in my calculator. I already had this in at Y1. I had done Y2, Y3, and Y4, I believe, so I put this in at Y5. So then I defined a new function, maybe Y6, as W prime minus A prime, which would be like taking, the derivative of the previous functions that you had in the Y equals buttons. If I've made that more confusing than it should, I apologize. Anyhow, if you put 3.5 into these, you're going to get this is negative 1.4, negative 1.143, and what matters is that it's negative. It's less than 0. That means that the slope is going down. That means that the graph is, or the curve is going down. That means the graph is decreasing at 3.5. If any of that didn't help, or if you have more clarifications for this, please send me something on Remind.